Last week we did like what is the internet, and next today basically we're going to do internet hardware, and then next week is internet addresses and viewing websites. So you basically have we will basically cover a unit of a class during this course. I'm going to start by kind of going over briefly what we did last week for people who weren't here to know. So basically, we were introduced to what the internet was, which is a network of networks, and it's built upon protocols. And here, the internet's very big, as we all know, and then there's many functions of it, which is here, collaboration, communication, dissemination of information, crowdsourcing, anonymity, censorship. We did a few activities regarding each of these. We looked at some entertainment, and here's the activity. I think these lectures are all posted on YouTube, and if you want to look at them, you can let me know. Yeah, but basically that's what we did last week. And let's start with this week's lesson. So this week we're going to be talking about internet hardware. So internet hardware. I have a Google form that you guys can follow along. So try to fill out these questions as we go along, just for a way to engage yourself. Let me put this link in the chat. Yep, so by the end of the class, you should be able to fill out all of these questions. Okay, and let's start. So last time we covered what is the internet, which we know that it's a network of networks. So if we know that the internet is actually a network of networks, then let's start by defining what a network is. So basically, a network is a group of two or more computer systems linked together, as you can see from this image. So for example, if I want to send like this smiley face emoji to the other computer in the network, then for example, if there were like a direct connection, I can just go ahead and send that. Okay, so I want to start with a term that we have here, which is called scalability. So the dictionary definition of scalability, if you search this up on the internet, it's the ability of a computing process to be used or produced in a range of capabilities, or I like the second definition more, which is measure of a system's ability to increase or decrease in performance and cost in response to changes in application and system processing demands. That's a mouthful, but what it's basically saying is as the system becomes bigger, meaning that it performs more tasks or processes more items, then the system should be able to keep up with it should be able to process more applications in a reasonable amount of time and under a reasonable amount of cost. So you don't want it to cost too much. And this is a very important concept because when you're developing softwares, when companies are like doing anything, the startups, when they're making their systems, scalability is a thing that they have to consider. So here we have some examples of scalability. For example, how well a hardware system performs when the number of users increased, how well database withstands growing numbers of inquiries, and how well an operating system performs on different classes of hardware. Okay, yeah, so basically, as if you were like Amazon, for example, Amazon probably started out as a really small shop, and then as it got bigger and bigger, they had to keep on upgrading their system and their scale, increasing their scalability so that more users were able to use it without the website crashing or anything. Okay, so let's apply this to a network, which is basically essentially the internet. So how do we scale networks? As we increase the number of computers in a network, there needs to be connections between each of these computers for them to communicate. So as we see with the smiley face example, if I want to send, let me annotate. If I want to send this smiley face from this computer, that's a really horrible one. It's like a frowny face. And to each of these laptops, there has to be these lines, these direct connections between them. And of course, if you know anything about internets, we don't have that. We don't have direct lines connecting one computer to another, and we're going to know exactly how we do that. So with this solution, with all the networks connecting, it's not very scalable. So it's not a very good solution to our problem since there's like billions of devices connected to the internet, and it's not possible for every device to have a direct connection to every device. Like, think about how horrible that would be. Um, yeah. So the solution to this problem on a small scale is to connect each device to a central hub. And this hub is referred to as the router. So you guys all have routers at home, so you've probably seen what it looks like. But basically, instead of these individual connections between laptops, all of these are connected to this one router, like a central processor that will allow the computers to communicate with each other. Okay, so let's talk about specifically what routers are. Routers, they connect different networks together. They send data packets between networks in form of IP packets, and we're going to talk about IP packets more in the next class. Routers have a routing table in it that's refreshed periodically according to changes in the network. As you know, there's like lots of data, and this is also how our, like, through text message or through any type of social media, a message gets sent really fast because these routers are always refreshing and sending you new information every like millisecond or nanosecond. They also provide protection against broadcast storms, and these are actually pretty expensive, and they're more expensive than other networking devices like hub bridges and switches. I'm not sure what those are, but I guess they're like alternative ways that laptops can connect to the internet. They're probably something we don't really use anymore since routers are so much more accessible now. And they're manufactured by like Cisco, D-Link, HP, 3Com, some very familiar companies, and you definitely have routers in your own house. So a single router can connect to a good number of devices given that they're close enough together. So generally, a small network would be able to compass the devices in a single room or building. So you could say, oh, how like the question here is what is the scalability essentially of the router? And the answer is that it's not very good actually because you have it's only the devices in a room or a building. Again, there's like better routers and worse routers that are manufactured. So yeah. In your own room, in your own house, you probably have one of those. It's like the things that blink. That's like a tiny box that you can connect to the internet with. Let's say we want to send a message from our computer from home to one at school. Like, it's a pretty common task. So how exactly would you be able to do this? And like I said, somehow we have to connect all these networks with some sort of direct connection, like these imaginary networks. So what we do is that we can add a router to connect these separate networks. So now you can kind of see what we're talking about, which is a network, which is one network. We have these individual networks, and together they're one big network. And that's essentially how the internet works. And it's not necessarily more work for this one router because they're only receiving signals from like these four. Okay, so again, as we increase the number of networks, the router connected starts to get overloaded. So again, this solution is not very scalable. Despite routers being like one of the most common ways we can connect to the internet now, it's not a very scalable solution. So people are also constantly looking for like upgrades to routers and like better ways we can connect to the internet and for the system to become more scalable. So this poor router is getting overloaded with too many signals and too many requests. So, and there's also other networks that would need to be connected. So what do we do? Does anyone have any ideas? Any thoughts of how we can solve this problem? More routers. Yes, exactly. That's a great guess because that's exactly what we do. We just add more routers to this. So and that's exactly how the internet works. You have a huge network of routers that connect to each other. So here we have however many, and yeah. So now not every router is connected to every other router because each one is connected to a few others and they're all eventually interconnected. So for this one, you don't see like 1, 2, 3, 4, 5, 6, 7. You don't see 7 lines coming from this one, sorry, this one router. Instead, if we want to go from, for example, this one to this one, we can like go in many different paths. We can go from here to here. We can like take another path from here to here to here to here to here to here. So there's a lot of ways you can get to this. And this again is really good because let's say like one of these routers breaks down because there's too many requests or something, then you have other routers that can take the place of it. So you have a redundancy between these paths, which allows us to use the internet whenever you want, even when one of these routers is down. Okay, and then individual networks can then connect to the internet by connecting to a single router. And this connection is often facilitated by an internet service provider or ISP. So from one to another, if this, let's say, if this laptop, if this laptop wants to communicate to this laptop over here, we can go from here, 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 and here, and here. Or if we can go here, 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 here. So there's a lot of ways that we can get to there. And with more routers, there's like even more paths we can take. And I want to explain an internet service provider. So this is what we normally use on our phones for data, like AT&T or T-Mobile or those kinds. They're all internet service providers. So they are essentially what they are the people who would try to fix these routers if one of them goes down, and they probably have storages for all these routers in somewhere and for all these signals to travel and to facilitate this. Next. So right now, we don't really need to focus on this huge interconnected cloud of routers. We can just abstract it and call this the internet. And yeah, these routers would all be the internet, and individual networks like our homes, our school, Starbucks would all be connected to what is essentially the internet. And then again, I just want to emphasize the how important scalability is because enterprises, if you're planning on your business to grow, which I would be everyone, you want it to grow rapidly, and you should pay special attention to scalability when evaluating both hardware and software. So next we're talking about sending information because the core function of the internet, it's what it's originally and truly designed to do, is to send information. Like right now, We have like different, like I talked about last time, we have collaboration and crowdsourcing. But essentially, the most important part is for people to communicate with each other through our laptops. Even though you can like access, I feel like whatever you do on the internet, like communicating is a big part of it. So um, yeah. So anything you do on the internet is essentially socially communicating, which like there's a topic about this on human learning, and I think that's very interesting. But yeah, that's not part of our lesson today. So again, if you want to send this smiley face to, oh, okay, I guess we can go here. So if we want to send this smiley face to the second laptop, then we're not just sending a physical smiley face, but we're actually transmitting some binary code. And we're going to introduce the concept of binary later. But yeah, so, what we're sending is not just like a letter or a mail, something that's physical, but it's something that is abstract and that you can't really see. So, exactly how do we send these information? Oh, yeah. And it's also something someone said counting in binary is surprisingly simple, easy to do, and it's also pretty essential. And if we have time, which I think we will, we can also talk about how to count in binary and like hexadecimal and decimal. So basically, the way that we count isn't like the only way we can count, which is really interesting. Um, yeah, so we want to send this and we go through all these routers. So one of these dot represents routers or networks, and then we can send one to the other end. So yeah, like I said, all we need to do is get digital information from one computer to another. So now we're going to talk about the different methods that we can actually transmit those bits. So there's three primary ways we can transmit digital information, meaning bits, which is like either a 0 or a 1. Let me talk about this first maybe. So basically binary. So really we have binary numbers or systems. So when we refer to binary, when we refer to binary numbers, we're usually referring to either a 1 or a 0. And then we have this counting system that we use that will make up these binaries. So usually we count, for example, if we can send a message, we want to send 101010. And basically this 101010 can mean, let's say it means hello. For some reason, this stream code means hello. So we have to basically send this instead of this, because the binary is how the computer communicates and language is how we communicate. So you want to send this between computers. So, and now this is considered digital information. And now we're going to consider how we're going to send these binary numbers through computers. And we have three ways that we can do that, which is electricity, light, and radio. Okay, so let's first talk about sending bits with electricity. As you can see from this picture, it's something you've seen before, probably like years ago, 10 years ago. It's a very old traditional way of sending information, and it's called the Ethernet. So the most common cable used by modern computers for transmitting information through electricity is this Ethernet cable. Some good things about this cable is that it's cheap, it has a faster connection, it's more reliable and secure. However, on the other side, it only covers medium distance. It's a non-deterministic service. So what non-deterministic means is that it exhibits different behaviors on different runs as opposed to like a deterministic algorithm. Um, Sorry, let me correct this. So basically, what I'm trying to say over here is so what it's basically saying here is that um for this for different behaviors on different runs, there they will so for the same inputs, there will be different behaviors on different runs. So for example, if you were to say, I want to send a smiley face, the universal example that we're going to use, if I want to send a smiley face across the internet, sometimes it doesn't do that. Sometimes it like misses like a dot or misses part of it, and we just don't really know what it's going to do. And this is also not good for real-time applications. For example, if you're like streaming, if you're playing a video game, and there's a constant exchange of information, the Ethernet cable is really not good for that. And you've probably seen these cables around your houses or something like um they used phone cords used to have these cables when you would like have cord home phones that connected to cords, and then like that cord would be connected to the wall, which would be connected to a router. Yeah. So, yeah, this is this everything that we talked about before still applies in this case, but it's just an older way of connecting to the internet. So let's talk about like exactly how we can send these bits, these zeros and ones with the internet. So the most common cable used by oh, we already said that. So sorry. So to send a one via electricity, we have to send a signal with a high voltage, as you see here. So we have um, a laptop, and then we like for just give it a high voltage, and again, this conducts electricity and sends it to the other laptop. And then a zero, we simply send a signal with a low voltage or no voltage at all. So for example, if we were to send a 1010, it would be high. Oh, I think I have an example of that later. We'll get to that later. Okay, so sending bits with lights. So the second way that we talked about is through lights. So when we want to send digital information through light, we have to use these fiber optic cables, as you see here. And they look very cool. They look very high tech, but they're actually not the most common way to do it, even though they are a very good alternative. So the pros of these is that we can cover very long distances. They're more scalable. If you want to add more, you can just like connect more cables together, and then you'll have more. And then they're very secure, which is really important because we'll also talk about this in the future, but like with cybersecurity and all these new fields emerging, we want to keep our data set um, we want to keep our data sets safe from other like hackers, for example. So this is a very secure way to do it, more so than the last the last the sorry more secure than our current way of sending bits. However, it's also very expensive, as you can probably guess, and it's very prone to physical damage. And on to know this, I want to talk about like how we communicate internationally. So basically, we have private corporations will like lay down like lines of internet cables just through the ocean. Like they'd have these robots that go under the ocean and lay down all these lines. So there is some kind of a communication between us and, for example, Asia. Um, so the way that we do now, which is through, let me skip this, which is through radio wave, it's it's not a very long distance, so we can't really do that. So instead, so what's under our ocean is actually lots and lots of cables that literally connect us from one router, for example, in America to a router in England or something like that. So I just think it's really cool that private corporations are the ones who do that, and that like when we're communicating is with like another country, it might be essentially sending messages through underwater cables that can withstand a lot of pressure, which I thought was very novel. Okay, yeah, that's a very good point. But fiber optic cables, they are relatively strong, but still, like if you were like, I'm sure you like usually it's just like a person doing it, but if you were like to like accidentally crush it under something, it's more pressure, I guess. Yes, exactly. It's even though it's more prone to physical damage than other things, but yeah, it's still very strong. Still, a lot of people still use this. Yeah, and it's expensive, which is the other thing. If you would like to send information to someone, how would you know? Send information somewhere, how would you know? Okay, so basically, what we're using most of the time is radio, which is over here, and we'll talk about that. And these are like the cell towers that you see in other places. But but if you're sending, but if there's like no cell towers, or if you and the other person are located like further away, then it has to go through another, usually another way. But you don't know, essentially, you wouldn't know which method is being used because the internet service provider would know that. Yeah, if you're, I think fiber optic are the underwater stuff I was talking about. So I think it's cool how like the ocean basically lights up essentially if you send like a piece of information across these. Yeah. Okay. So to send bits with light, it's basically the same. Okay, yeah. Sorry, wrong slide. So to send information with light, it's basically the same way that we send information with electricity. So we send a bright light through the cable if we were to transmit one, and if to send a zero, we would like shine a dim light or basically turn the light off over here. So let's talk about radio waves, which is the most common way to usually send information. So if we don't want to, if we want to send information through radio waves, we don't need cables at all. We just need a Wi-Fi router or a cell tower. The thing about this is that we it's all wireless, so that's why we don't need anything connected to our laptops. We can have data everywhere. But the bad thing about it, it's very short range. So like if you're in the mountains, as you know, or like if you're really far away from a cell tower, then you won't have access to Wi-Fi. It's really interesting because Morse code was how we sent like if you say like long, short, long, that's how we sent a message. But basically, yeah, exactly. It's kind of how Morse code works, but binary is just one of the ways that we developed it. There's like other types of conversions that we can use too. So basically, we can send like hexadecimals as well, which is basically a number system based on 16, and then it can translate to like AS. I think it's called, I'm not sure what it's called, but it's like for example, 16 would correspond to A, and then you have like a number system like that. Yeah. So again, it's really similar how we transmit in bits with a high frequency, we can transmit one, and then to signal a 0, we can just translate a wave of low frequency, and that's basically how they communicate. So let's say this is the example I was talking, sorry. So this is the example I was talking about where we want to send 101, wait, 1010. So basically for 1, we would send the higher voltage one, which is in yellow, and then we would send the lower one, the higher one, and the lower one. And there we go. We can send this message through the computer. But does anyone notice a problem with this, or like somewhere where things could go wrong possibly? Okay. Yeah, so what happens with this, yeah, if a computer missing a bit is also a thing, which is like a which would be basically you're in like a sentence, you're missing like a word, and then like you wouldn't know what it was talking about. But the bigger problem is what happens if we want to send like two binaries that are the same. So for example, 10001. So if we were to send 10001, what would happen is that we would send 1 high voltage, and then 0 a low voltage, and then another low voltage. But there won't be a difference between any of these, if you know where I'm going with this. And now we have a disconnect because we don't know if we're sending 2 of the same ones, or is it just sending 1 of the same thing. So to solve this issue, we can use a clock, essentially, which will allow computers to agree on how often to send or receive a bit. And for example, every second, the computers would agree to send 1 bit. So first second, it would send a high voltage, high frequency, or like, yeah. And then the next second, they would send no voltage, and then the next second they would again send no voltage. And now because there's a clock, we know how often we have to receive the message. So now it can work. So with this example where we transferred 1 bit every second, it's very slow, and computers are actually a lot faster than that. So the amount of data that can be transferred by a single system is referred to as the system's bandwidth, which is a term you might be familiar with. It's measured by byte rate, which is the number of bits that can be sent or received by a system in 1 second. So basically, the higher the bandwidth, the more data can be transferred. And here I want to give like a relative information about how fast the internet is. So we have one byte, which is like I said, it's a binary. It's either a 0 or a 1, and then we have 1 byte with a y, which is equal to 8 bits. We have 1 megabyte, which is 1 to the power of 6, so this much, and 1 gigabyte, which is 1 to the power of 9, which is this much. And I think what is considered like a high bandwidth is, what's considered a high bandwidth is 5 megabytes per second over, I don't know how to make this bigger, but anyways, yeah, that's usually how what's considered like pretty fluid. So it's a lot of data that can be transferred. And yes, Mbps is usually how we write it, megabits per second. Okay, the last thing I want to talk about is latency. So The latency is time that it takes for one bit to get from the sender to the receiver. So when you have low latency, it's actually a fast connection because you will take less time for the information to transfer basically. And fiber optic cables, they have the best latency. They can transfer data at the speed that light moves through glass. So not exactly the speed of light, but the speed in which light moves through glass, which is 5 microseconds per kilometer. Yes, 5 microseconds. Does that make sense? Yeah. And then Ethernet cables, they have a latency of 300 microseconds per kilometer. And although usually Ethernet cables don't go up to 1 kilometer. So our next thing is going to be sequential, parallel, and distributed computing. So like, because we talked about like the internet and communication, I also want to talk about like how our individual computers would process all the information sent.
Like binary?
Yeah, like binary.
What about hexadecimal and octal?
Yeah, and I want to talk about those systems too and how you can
Are there any
basically
other systems other than those?
you can count in any system. I don't know the names for all of them, but you can count in anything that you want. Does that make somewhat make sense?
Base 3?
You can count in base. Okay, let me just explain this now. So let me try to explain how to count in systems basically. I can do binary, and then if you know how to do hexadecimal or anything else, you can go ahead and do that. So basically, how we count is in decimals. So we have, for example, 12. We would have base,
Base 10's the normal way, right?
yes, base, we count in decimal. So decimal, deci is usually 10. So we have 10 to the 0, which is 1, 10 to the 1, which is 10, 10 to the 2 second, which is 100, 10 to the third, and that's where I'm going to stop, but there is more. So 1,000, 100, 10, and 1. So basically, if we were to write the number 12, we would have two ones. So that's why we would put the 2 over here, and we would have 110. So you would essentially think of this as 10 plus 2. Mm-hmm. Yeah. So this, and then we would have 110. And yeah, so I'm going to move on to binary in a sec. So this is how we normally count, except we don't really think of that much because we basically internalize it. So you can count in whatever system you want. When do we ever use this? Computers. Usually this is in computer programming. You use these a lot in your projects. I don't have binary. We have a specific example, which is the internet, but other than that, it's if you want to like program an array that has like certain rows and columns, it's also a very useful way to do that. No. Well, you learned something new today. Okay, so let me keep on explaining this. Yeah, some of them are more common and some of them aren't. So 2, 8, and 12 and 10 are the most common, I'd say. So, okay, so if we were to do the number 100, 1,200, we would start with the highest level, so there would be 1,000, and then you still have 200 left. So what would the 200 go into? Let me erase these two. So what would the 200 go into? And 200 would actually go into, go into here. So there would be a 2 here, and then these would be 0, 0, because we don't need a 10 and we don't need a 1. So, okay, this is how we usually count, which is pretty simple. But let's look at another example now. I'm going to switch color, and now we're going to talk about binary. So binary, again, we're going in base 2. So we have 2 to the power of 0, which is 1. Oh, I should just type this, shouldn't I? Okay, let me type this. We have 2 to the power of 0, which is 1. We have 2 to the power of 1, which is 2. And next we have 2 to the power of 2, 4. 2 to the power of 3, which is 8. And I'm just going to go up to 2 to the power of 4, which is 16. So let's say I want to do writing what we think of as 10. Let's say we want to write 10 decimal. So this is the symbol for decimal because it's 10 into binary. So base 2. So what you have here is, let's start from the highest one. Is there a 16 in 10? There isn't a 16. So we're going to skip that and we're going to go to the next one. So, which is 8. So there's 1 8 in 10. So we're just going to go ahead and put that as 1 because there's one of them. And then if you do 10 minus 8, you still have 2 left over. So you go directly to the 2 and you go here. So this would be 1, 0, and then you fill in the rest of the spaces just like you were if you were writing a normal number. And here, this is the 1, 0, 1, 0 is basically the equivalent of 10. So from here, and then and then you can keep on going with this binary 2 to the power of 5, 6, 7, 8, and so on, and then you can translate bigger and bigger numbers. So usually computers would process in like strings of 8. So 2 to the power of 8 would be the biggest one. And then if you do, for example, we want to translate 1 1 1 1 1 into decimal, then what you would do is, let me write this. So writing the ones correlating with each of the columns. So you would do 16 plus 8 plus 4 plus 2 plus 1. And can anyone tell me what that is? 16 plus 8 plus 4 plus 2 plus 1. I'll come to that. Yeah, 31. There we go. 31. So 1, 1, 1, 1, 1 in binary is 31 in decimal. And then I'm just going to introduce these number systems for today, but if you have, maybe if we had time after class, we could work on hexadecimal. So does that make sense to everyone? Give me a thumbs up if that kind of makes sense to you. Now that you guys get this, let me put the Google survey in the chat again, because you guys were supposed to fill this out, but if you missed it, I guess that's you can fill out the questions that you can answer, or like that we haven't went over, or like if you missed them, just you can say you missed them, either if you left early or I didn't tell you earlier because it's my fault. Okay, so let's go back to this, our main lesson. So sequential, parallel, and distributed computing. So like I said, once you have the internet, which is communication between computers, we're going to talk about how your own computer would process these tasks that they're assigned with. So each of these different styles of computing dictates how a computer goes about finishing its tasks, and we'll look at sequential computing first. So with this type of computing, each task is done one at a time in the order that they were fed to the processor. So for example, we have these 4 tasks to complete and we have these results. So what would happen is basically Let me draw on this. Task 1 would go first. It would go from here into the processor. It would lead to this result. Task 2 would go second into the processor, this result. Task 3, this processor, this result, and task 4 into here. And it is only when one task is finished that the second task can start. So the second can't start until the first one is done, and that's sequential computing. So depending on the number of tasks, this is fine, but as the numbers grow bigger, the computer would take a long time to complete all of its tasks. So if we needed to complete 100 or 1,000 tasks, this would definitely be the slower approach. Yeah, so basically this is like just a normal approach that we would use, but there's others that would definitely speed this process up. If we want to spread the load between all of these computers, we have what is known as parallel and distributed computing. So with these two styles, we divide tasks up that need to be completed, and then we'll assign them to different processors and smaller subsections of the workload. So parallel computing is most often computed with the same computer with shared memory, and distributed computing is used with different computers and which would need to communicate with each other, often through the internet. But the most important thing about both of these is that they would need to use more than one processor to accomplish their tasks. So parallel computing would use like the same computer but two different processors, and distributed computing would directly use different computers. I think we talked about this last time, but this is also where crowdsourcing becomes pretty important. Last time we looked at that like protein folding example, and basically what happened was that like each volunteer would be able to run a section of code on their own laptop just for charity, for volunteering, and then they would send the information back, and then they would put all the protein information together, and then they have their own research. So this definitely speeds up a lot of processes. So let's first look at parallel computing. Um, so if we look back at our example, we can see how parallel computing is used to solve a sequence of problems. So we have task 1, and which is fed to processor at the same time that task 2 is fed into a processor. So because we have access to both of these now, we can complete 2 of these tasks at the same time, which is obviously if you complete 1 and 2 together and then 4 and 3 together, you would take half the amount of time it would usually take, which is good. We want to take less time. Okay, but the bad thing, the challenges when we use parallel computing is that it's harder to find where an error happens, and if you've done like any like coding, if you tried any coding or programming, you'll know that like one of the worst parts about um, coding is finding where you went wrong, because sometimes it could just be like a colon or like a punctuation thing, and you don't know where it goes wrong. So it would be really difficult to know what happened in between. So again, if we do 1 and 2, tasks 1 and 2 at the same time, you won't, it will just come up with an error that says, oh, there's an error in your step 1. But how would you know that it's like 1 that went wrong or 2 that went wrong? So again, you'd have to like run this separately, and that also takes up time. And basically what you'll end up with is kind of sequential computing anyways. And but again, in the grand scheme of things, it'll definitely still be less time, because not all tasks would have a error, and if you have like 5 pairs of tasks and you have error on step 5, you just need to check those two, and you don't need to check anything before that.
Don't you have to well, if it's faster, doesn't it mean that it's gonna be more complicated?
Yeah, it is. Actually, what do you mean by more complicated?
Like it's the like if say you have a code and you're trying to run it, like you have different types of code, and then they give the same result, but one is faster than the other. So the one that's faster doesn't need like more steps or
If you're talking about time as a definition for complexity, then I mean, when task one finishes, the even if task one finishes before task two, this first processor can move on to four while two is running. So for example, this processor one will basically finish quicker than this second one. Okay, for example, let's if you're I'm not sure if that's what you're asking, but if you say like complex is like the time that they're running, not like necessarily amount of code, then this is how it'll work. So, for example, task one might take, sorry, task one might take 20 seconds. Task two could take 30 seconds. Task four, 10 seconds. Task three, another 10 seconds. So it would go task one goes in, and then it would start on this. So by the time that task two finishes, both of these will be finished. And that's fine. You'll just have a processor that does nothing for 10 seconds. But again, there's like smarter ways. And I think you bring up a good point because there's like different ways that you can arrange these tasks for them to be more efficient. For example, if I want to arrange, let's say these were different times. Let me think about it. If this was 50 seconds, if task one took 50 seconds to, sorry, if task four took 50 seconds to run and task one took only 10 seconds, you wouldn't necessarily want to distribute your tasks like this. So instead, you could just say, I'm going to assign task four to this processor and two, three, and one would be into this processor. So then they would finish at the same time and yeah, produce the result that we want. Does that kind of make sense? Does that answer your question? Okay. Um, yeah, so these are actually like questions that will come up on the AP exam if that's what you choose to take. So they'll give you like times of each task and like ask you how you want to arrange them for them to be more efficient. So let's move on to the next one, which is, and basically when you compare sequential and parallel computing, it's easier to locate the error in sequential because only one task is accomplished at the time. Um, Another potential complication within parallel computing is that the architecture and SEP is pretty complex. If one task relies on another task, it could cause lockups and you want to do some then first. So for example, in this example, we have task A, 1A, 1B, 2B, and 2A. So what would happen? Let's see if I have some. Okay, so what would happen with this is basically we have to finish 1A before we go on to 1B. So we take this one to this processor, and we can't go directly to this. If we did assign this to this processor, it won't. That it would give us an error because we can't, because the the input of task B might rely on the output of task A. So what I mean by this is, for example, task A gives us a result. Let's say our result from task A, 1A for whatever reason is 3. And this is inputted into task 1B. And then 1B has to take this and then compute like another result of its own. But without this input, task B would not know what to do. So when this scenario arises, what we have to do is feed 1A into the processor and then 2A into the processor. And after these two are complete, we can feed 1B and 2B in. Does that kind of make sense? You can give me like a thumbs up or something. If you guys learned in math class of functions, I think this is a good place where functions come up. For example, I think you guys, this basic algebra, you guys probably should have learned this, but yes. So basically we have like f of a function of a here. And then this is basically f of, and then let's call this, sorry, not f, g of, oh, sorry, let me just type this. Drawing is horrible. F of a equals to certain function, let's say a plus 2 as an example. And then here we have g of a equals to f of a plus 3. So in this example, we need to compute with this function f of a and then put it and input it into here, and then we get our results. Okay, let's move on. So here I just want to summarize the pros and cons of sequential and parallel computing. In sequential computing, the tasks are slower and it completes tasks in order. Sorry, and completes tasks one at a time in order. But with parallel computing, it's usually faster. There's like that exception where I talked about where tasks are dependent on each other and it completes tasks simultaneously. But the difficult thing about parallel is that it's difficult to find bugs, whereas in sequential, it's easier to find bugs. And it's also more difficult to set up to use, and it's more difficult to use and set up correctly than sequential. With sequential, you just need one laptop and no additional setup. Okay, so let's talk about distributed computing, which is our last subject. So parallel computing can be paired with distributed computing by using more than one computer. And let's say we have, that's not a tune, that should be a ton. Let me just quickly correct that. We have a ton of tasks to complete. We could try to improve the processing power, and that gets expensive. And there's also limits to how fast a computer can run. Instead of a computer, we can split the work between multiple different regular computers. And this still technically counts as parallel computing because we're using one processor. So what this means is that a processor usually refers not to as like a computer as a processor, but like CPUs, for example. So in some cases, I guess, you could have like one laptop can have two different processors or something like that. I don't think it's common. I haven't really looked into that. If you know anything, you can feel free to look it up. But yeah, but there's still like a limit to this processor for, so you can improve the efficiency of individual processors, but only to a certain extent. You don't want to put like too many processors in or cores in one laptop because you don't want them, your laptop, a very common example of this is when they overheat and like your application quits, and you don't want that because it's like a router, your processor's basically being overloaded. So that's the limit that we want to avoid. And also It's more difficult to improve processing power than it is to add more computers. Like you have to like research and like that's a whole different realm when you like research into processing power. Yeah. So instead of one computer, one processor, we split the workload between different computers. And yeah, basically they all run different parts of the code. For example, you can like run a certain part, I can run a certain part. And when you like put them back together, like often through the internet, that's part of the collaboration of internet. You can like have this whole piece placed together. Yeah, and again, this still counts as parallel computing because um, distributed computing would like kind of be a subsection of parallel computing. Okay, so let's look at an example here. So we have one computer that shuts. Let's see if I can see. One computer that shuts down and can't process. So this computer is out. It's done for today. So we can reroute the tasks that were assigned to that computer. So um, we can we can reroute the tasks that were assigned to that computer to one that is working. So that's the good thing about distributed computing. You have like um, redundancy. You have it's fault tolerant, and it works in a way that's pretty similar to the internet where you have redundant and fault tolerant capabilities. This is also good because it's more scalable. Another definition that we talked about earlier. So we can easily expand a distributed system if the workload increases. So when we have, for example, we had 3 computers in, it's really easy to just basically add another computer. It's not as much setup that's needed for parallel computing where you have to set up different processors. So for example, if we had like a supercomputer, we would have to shut down a program and try to upgrade the computer to be able to handle the increasing task load. Because of course, it's just one computer. Once that computer dies, everything would go down. And again, there's limits to the processing power of one computer. Okay, and this is the last slide, which is the benefits and challenges of distributed computing. So the benefits is that it's scalable, it's fault tolerant, and it's reliable. But the challenge of it would be that it's really complex and it's pretty expensive to maintain. And I think that's the end of the slideshow. Does anyone have any questions about any of these computing techniques? I think that's it for today. If you guys have any questions or something that you want, you can put it in the survey that I gave you guys. And once you finish that, you can go ahead and leave. I hope you guys have a great day.